So my name is Mats Johansson, and I will talk today a little bit on work we've been doing on lignin-based thermosets. But what I will do today is also start with a little talk about thermoset polymers in general, both synthetic and natural ones. And then I will also give some general aspects of thermosets and lignin, different approaches. And after that, I'll go into some specific examples of what we have been doing and end up with some outlook and what I see as challenges. So basically, if we start with thermoset polymers in general, that is, you need to start with a monomer functionality more than 2. So when you polymerize it, you will obtain a crosslink polymer. You'll form a network structure, and you'll have an infinite molecular weight. So it's basically one molecule. The properties of these thermosets will depend on different factors. And one of them is the crosslink densities, meaning that how densely you connect all these molecules together. But also very important is how the polymer structure interacts both internally within the thermoset structure and how it interacts with the surroundings. Thermoset polymers have a large number of application areas, and it's quite often when you need to have a specific mechanical property or shape. It could be, for example, composite matrices, adhesives, gels, swollen polymers that you should have a certain shape, like contact lenses, high performance polymers, and so on. So when you make a thermoset polymer, you get the structure formation by starting with something that is thermoplastic, an oligomer, normally molecular weight a few thousand, and monomers, which you polymerize into a final network. This can proceed in the same way as when you make traditional linear polymers. You can have a stepwise or a chain-wise polymerization reaction. And actually, these reaction mechanisms will also affect how the network is formed, and in many cases is very important, but I will not discuss that very much today. Looking into thermoset polymers, you can have a number of parameters that will affect the properties. You have the crosslink density, and that's the average distance between crosslinks. So at the same time as you have in a linear polymer, you have a polymer molecular weight distribution. Here you have a distribution of average distances between crosslinks. You got the polydispersity of this, so you don't have an exact tri-dimension network. But then you also have the chemical structure of the specific building blocks, and their important properties are rigidity, how stiff the chains are, and the polarity. Polarity will to a large extent affect non-covalent interactions with surroundings and inside the network structure, and I'll get back to that later on. You also have other factors, like if you have dangling loose ends of chains within the network, they can actually be internal plasticizers. You can have minor cyclization structures that don't really contribute to the network. And then it's important to see how homogeneous is this network on different length scales. And that is normally not considered that much, but I will get back to that here because I think it has an importance in this context. So traditional thermoset polymers, you start normally with a resin, what we call a binder resin or a pre-polymer. That's an oligomer. And in many cases, it has a molecular weight between 3,000 to 5,000 grams. And you combine that with other monomers and reinforcements. The reason that you start with a resin that has a reasonably high molecular weight is that it should be low enough so it allows for processing of pre-shaping a polymer in the thermoset, but it should be as high as possible to allow for not that much shrinkage when it polymerizes. So it's a balance about pre-processing and final properties. Within these oligomers that you start with, you normally have built them by monomers like polyester resin with the polyols and dicarboxylic acids. The monomers in these resins are normally randomly distributed. Important properties for thermoset polymers is, for example, stiffness, and a typical curve temperature dependence is like this. You go from a stiff material to more soft, the glass transition, and you have a rubbery state. The level of this rubbery state is very much dependent on the crosslink density. And of course, depending on the application, you want to have a correct temperature range for the transitions, and in high performance polymers, a rather stiff material. But you also have other properties, and one that is very important for thermosets is the elongation at break. How ductile is the material? Is it brittle, so it will fracture when you have a very low small deformation, or will it exhibit ductility, meaning that you can actually stretch it without breaking it? And this ductile brittle transition that you have for thermoset polymers, that is not the same as the glass transition temperature. The ductile brittle transition is to a large extent affected by the crosslink density. The more crosslink density, the more brittle the system is. So you have a number of different properties, ductility, strength, and stiffness, that is important. And of course, if you have any type of cross-linked network, then they can be considered as thermosets. So all polymer systems with a covalent network structure. So why lignin? Well, it's well known for high performance polymers, and especially thermosets, that you need this aromatic structure to give rigidity into the structure. And lignin is one of the few abundant renewable sources that provides aromatic structures. And then one can also, of course, why does nature use lignin in nature? And there's a multitude of reasons for this, but one is probably the mechanical properties, and that's a good starting point, I would say, for adding more functions and also understand how they work. So looking into the literature and what others have been done and we have been doing, you can have different routes when you want to address the use of lignin in thermoset polymers. You can break down the lignin that you retrieve from any source to monomers and subsequently use them in the same way as you do for synthetic polymers, meaning that you bring out a monomeric unit, you combine that with other synthetic monomers or resins and produce a thermoset. So that's a sort of a drop-in solution. And one of the most explored one is, of course, vanillin, that you can functionalize to be an acrylate or other components. The disadvantage with this approach is that it takes some effort to refine the monomers and retrieve them efficiently in purity, and that adds cost. And then you also need to present an added value of using this specific monomer, not only as a renewable, but with a respective function. An alternative route is to utilize lignin, technical lignin and technical lignin fractions. You don't break it down to monomeric units, but you have a larger entity of some type of lignin pre-polymer. And the advantage here would be that you would have more available starting materials, more readily available, but it's much more complicated to use them. You need a lot of characterization to know what you start with, and it is more difficult to assess the structure property relationship, and we'll see that later on. One issue here also is that you need to have a process of retrieving these fractions that allow it to be reproducible, so that you can, it's not a problem if you have a polydisperse resin structure that you normally have for traditional thermosets, but it should be reproducibly to retrieve them. Okay, so starting with technical lignin fractions, there is a lot of then possibilities. You have different sources, you've got softwood, hardwood, etc. Most of you know this. They have different composition, and that will of course affect how you can use it. For technical lignins, you also have a retrieval process. You need to bring the lignin out, and how you do that will probably affect what you start with. You can do the Kraft lignin via precipitation, like the Lignin boost, organosolv for cross-flow filtration, fractionation, etc. So you have a possibility here to vary the retrieval processes. And then, of course, you have the fundamental questions. How does this technical lignins differ, and how can we incorporate them into thermoset polymers? And what I would like to emphasize that if we start to understand this a little bit better, then we can probably get more added value and improve performance. The lignins, as I said, depend very much on the starting material. You have the typical monolignose, coumaryl, coniferyl, and synapyl structures. They are combined in the lignin with different types of linkages, but they are also present in different amounts in different sources. So already here you have a significant number of possibilities of different materials. And I will focus today mainly on softwood. But as you see, for example, here you have this coniferyl alcohol. You have one methoxy substituent on the ring, and that will affect the reactivity of the phenol. What will happen if you have the synapyl variety? Can we use that in the same way, and will the properties differ? In a technical lignin, you also have quite a variety of functional groups that you can use then to incorporate this into thermoset systems. You've got phenolics, aliphatic alcohols, carboxylic acids, etc. And of course, you can directly use these in systems that co-react with these types of groups. Or you can use these groups to functionalize, adding a functionality into the structure so that you can have other cross-linking mechanisms. So here you also have a lot of different routes to go, so to say. So what I will take as an example here is something that we have been working in, is to try to add a functionality to lignin structures and functionalize it in a way so we get a handle that we can use for further reactions. And the route we've chosen is to do allylation. We take an allyl chloride in this context, and we react that with the phenolic groups in the lignin to form an aryl allyl ether. And if we can do this efficiently, then we have a handle that we can continue to use in a different number of different ways. So we have sort of a platform chemical. We can do silylation reactions, we can epoxidize it, we can use it with thiols to thiolene chemistry and other varieties, or rearrangement to propanyl ethers, for example. So what we have been focusing on is the thiolene chemistry. So the question here is, can we do the allylation? Can we use it? Can we get the final thermoset polymer? And how does the property, structure-property relationship work? So to start with, and that's quite often what you do, you start with developing a synthetic route and optimize that one. We started with the principle of starting with a monolignol, in this case coniferyl alcohol, and looked into a chemical transformation where we allylated this phenol and got a product looking like this, an allyl ether of coniferyl alcohol. And here, of course, the product here would have two double bonds. And if we combine that with a crosslinker, we can form a thermoset polymer. We can verify also on model substances that this reaction works very well. We can optimize the reaction conditions and characterize the systems rather accurately. So here we can see that we have can produce a selective reaction. We can have a possible thermosetting systems. We get a very high conversion, almost quantitatively, and under rather benign conditions. This reaction is made in ethanol, and you produce sodium chloride as a product. So it's reasonably good. And this allyl chloride, it's already used in industry as a synton for making allyl ethers. So it's established techniques. So we have then sort of what I call the drop-in solution. We create a difunctional monomer that we can use to make thermoset structures. If we then combine this with a thiol monomer, which is this trifunctional mercapto structure, we can do the so-called thiolene reaction, where you have a free radical reaction where the thiols adds to double bonds. And by triggering this with photoinitiators and UV light, we can polymerize this to become a thermoset polymer. So this is an example of how you can make a lignin-based monomer to use in combination with other monomers to make a lignin-based thermoset. This is of course rather tedious of making, purifying coniferyl alcohol and then making the monomer. But in principle, it works. We get nice freestanding films or materials with a TG around 20. We can measure the polymerization. It polymerizes very well, and we get high conversions. So it works fine as a building block in thermosets. So taking this further on to looking into the lignin fractions, here we have all these varieties and variables we can work with. And what we chose here was to start with softwood. We got Kraft lignin and Lignin-based lignin, and we could employ solvent fractionation to get different fractions and utilizing thiolene chemistry to obtain thermosets. So the question here is, can we use the same principle as for this monolignol to apply this to lignin fractions? And as you see here also, you already here have a lot of different other possibilities that I will not talk about today. So starting with this solvent fractionation that was developed by Duval, Lavocco, Christini, and others, we can take this Kraft lignin and we can technical lignin, we can solvent fractionate it and get a series of different lignin fractions with increasing molecular weights. We get more narrow molecular weight distributions. So what you do is you actually take the Kraft lignin, you solubilize what you can in ethyl acetate, and then take that fraction apart. Then you take the remainder and solubilize what you can take in ethanol, and so on and so forth. So we get this series of different lignin fractions. And what says insoluble here, it's insoluble in these solvents, but it's soluble in DMSO, for example, so we can measure the molecular weight of the starting material also. So here we start to have a sort of a library of lignin fractions to see if we can employ in thermosets. And the question here first, can we do the same functionalization, the allylation on this type of structure in benign conditions and get the resin? So yes, with a little bit of optimization of solvents and conditions, we can see that we can do this allylation on the phenolic structures in these lignin fractions. Also, what is good then is that there are techniques developed to monitor this. So this is I think, phosphorus NMR showing the different types of functional groups in the lignin. And we can see that we convert all the phenolics, or a high fraction of the phenolics, they disappear and we get this allyl product. So it works to do the modification on technical lignins. And we also see that on a slight increase in molecular weight. But we retain to a large extent the polydispersity from before. And also if we do NMR, HSQC NMR, if there's any questions on this, you have to ask Martin, because I'm not that good in that. But what we can see here is that with the starting material, we can verify that we have the allyl ether incorporated. But moreover is that we retain quite a lot of the original lignin fraction internal structure. So it's a rather mild conversion on these fractions. So question then, can we polymerize this together with a thiol as before? And yes, we can do that. There should be a peak here. I'm not sure why it disappeared, but we can see that we can convert the thiols and the alkenes to form a thermoset network. The question now arises, how does these properties of this polymer relate to the structure? And in order to more reveal that, we did the same functionalization of the different fractions. So here we now have a series of different increasing molecular weights. We also have control of the numbers of phenolics, different types of aliphatic alcohols, and the functional groups in the system. And we can produce, in this case, 4 different thermoset resins. Taking these, polymerizing these together with the thiol, we get 4 different types of thermoset polymers. And how do they differ in properties in relation to what we started with? So what we could see is that we get rather different properties for the different fractions. We could see that we got a reasonably high modulus in the GPa, gigapascal region below Tg, and that's quite logical. So it's a rather stiff material below Tg. We got higher molecular weight, fractions give higher crosslink density, and we see a shift, a rather strong shift in glass transition temperature. It should be noted here that the volume fraction of thiol monomer and lignin monomer is approximately the same in all these samples. So the differences here must relate to the different crosslink density or the internal structure of sort of lignin resin we start with. And lower molecular weight, we also see that we get a more narrow transition here. So we do see significant differences in final properties. Can we compare this? And that is the key question here. Can we compare this to conventional thermosets? Or is it other reasons than the traditional ones that makes these differences? So in order to reveal more about that, we started to look into morphology of the crosslinked network using X-ray scattering. So to start with, we used SAX, small angle X-ray scattering, meaning that we look at rather large features in the scattering pattern, nanometer range, and looked into what we call the Gwinner radius, which is basically the size of a repeating feature within the structure. And we could see that we had different sizes depending on what lignin we started with for the different thermosets. So we have sort of fluctuations in density within the structure. And we get the more homogeneous material here with this high Gwinner radius. So this is basically a sort of a measurement of a repeating size feature. So on the nanometer scale. Then looking into WAX, wide angle X-ray scattering. Oh, sorry. We saw something different. So wide angle X-ray scattering, then we look at smaller distances. We could see that we found different repeating distances within the thermoset network. And we correlate that to what has been proposed in the literature, the possibility to have some type of pi-pi stacking or other stacking structures. So what we see is different distances. So we got this short distance of 4.5 angstrom and a little bit longer distances. And this 4.5 angstrom we correlate to pi-pi stacking. And what we can see that depending on what type of lignin fraction we start with, we have different relative amounts of this. So going down to the smallest molecular weight, we got less of this pi-pi stacking in comparison to the other ones. And this correlates to some extent to the difference in mechanical properties. So this could be one of the parts. And now I'm going back to what we take as traditional thermoset polymers, synthetic ones, where you have evenly distributed aromatics like isophthalic acid, for example, in a polyester, that they are randomly distributed. But when we start with the lignin fraction now, they are coupled internally in a way that it might allow more of these pi-pi stacking to occur within the thermoset structure. And the key question, of course, is, does this affect the properties? So There's a difference compared to conventional thermosets, and the combination of molecular weight and functionality of these fractions is important. We also see that we have sort of nano domains and internal pi stacking. The question then comes, does the covalent connectivity between these domains, the Thiol crosslinker, affect the properties? And that became a subsequent study where we took one of these lignin fractions, the ethanol fraction, allylated that one, and instead varied the connectivity between the thiol monomer and the allyl groups by having a 3, 4, and 6 functional thiol. We had about the same amount, around 67% weight percent of the allylated lignin, and had monomers here that we combined with different functionalities. Question here, do we see differences? Yes, we see rather significant differences. We see a shift in the glass transition temperature. We've got differences in the modulus also, and this is still something that we are exploring. We're not fully understanding this. We got different TGs, as you can see here, and it shifts quite a lot. So also here it shows that the connectivity in between these lignin domains will have a big influence. So basically we can start with different lignins, we can have different lignin fractions, and we combine it with different crosslinkers. All these interact together to give a final performance. Looking at scattering data, Sachs-Wax for these, we did not see any differences between the systems of this distance that we correlated pi stacking, meaning that this sort of internal structure is unaffected in the different samples here. So we do have the significant difference in macroscopic properties, and that must be due then to the connectivity to the lignin. So in general, what we can say that lignin precursors will have an effect on different hierarchic levels, going from this angstrom level pi stacking to molecular oligomer level, where the connectivity has an effect on the nanosize level. And we still lack a complete understanding of this, but we start to understand a little bit on these differences in different length scales. And I think we have to address these thermoset polymers in a different way than when we compare traditional synthetic thermoset polymers. So what I've shown here is just examples on, and I would like to emphasize that again, softwood, solvent fractionation, Kraft, lignin, thiolene chemistry. There has been a lot done on epoxides, acrylates, amino resins, using different types of lignin sources, hardwood, annual plants. So we have a lot still to explore and understand of these type of structures. But I'm quite positive that we will find more knowledge and new bio-based systems using lignin in future sustainable material. So, and then of course, if we understand it, we can design it, we can get an added value into the final products. So I just described one route, the Thiolene allylation route. There's others in literature, and I would like to emphasize there's been quite a few recent reviews. This is one example where you can find details on epoxy resins, acrylates, metacrylates, phenol, formaldehyde, etc. It's important here to note also that, in my opinion, one should always be careful to know and define what you start with in order to correlate what you can get in the end. So these characterization protocols for different lignin fractions is crucial to get a better understanding. And also, if you want to see more about this, this is just the recent Virtuous special issue in ACCS, Sustainable Chemistry and Engineering, all devoted to lignin. And here you can also find then extra information about what is the lignin structure in nature, this is still debated, and what is the structure of technical lignins of different ways. Analytical techniques, this continues to develop, and that's important to have accurate tools to do this. There's also great improvement in lignin biorefining, how you can retrieve different types. And this, of course, correlates to the scale-up performance. And then applications like what I talked today about thermoset polymers, but you've got lignin particles for various purposes. You can have them as additives or functions like picking up metal ions and so on. So there's numerous applications. So this was mainly a little bit of an introduction to the field, and I hope I convinced you that there's still a lot of things to do, and I hope we can continue working on this for a long-term future. And with that, I would say it has a great potential. We need traditional polymer science descriptions to understand it, and starting to have this different hierarchical level, I think we need to develop that part also. And we only started to explore it, so more to come. Would like to acknowledge a number of persons that has been involved in this, mainly Marcus and Juliana, working as a PhD students here. Martin Lavok, of course. Stefan Lundmark is very good in allyl ether chemistry, and all the others co-workers that has been involved, and Knut and Alice Wallenberg Foundation for financial support. And finally, I thank you for listening, and I will be glad to try to answer any questions if I can.